So if I'm going to talk about polyprotic acids and how they are the same or different than monoprotic acids, it starts with the simple appreciation that if I've got more than one proton site, more than one basic site, every one of those must have its own equilibrium ability to add or take away a proton. It must have its own K value to describe it. So if I've got two sites for protons, I've got to have a Ka for the first one, a Ka for the second one. Let's just number them, the Ka1 and the Ka2. If I've got three sites, I must have three K values, Ka1, Ka2, and Ka3. Here's another three sites, a Ka1, a Ka2, a Ka3. Notice as well that I can sort of rank these sequentially from the smallest Ka value, pKa value, to the largest. This corresponds in this particular case, pKa1 equal to 3.6 of the most acidic site, and this is the least acidic site. Really acidic, because it's 10 to the minus 2 or so for the Ka value. In the middle, 10 to the minus 7 or so for the Ka. Pretty darn basic, 10 to the minus 12. Here, a bit different, one acidic site and two basic sites that are approximately the same. See, I can actually take a look at my K values or my pK values and immediately know about the compound I'm working with, whether I'm working with acidic protons or basic proton sites, just by looking at the Ka values. Now, having said that, if I write down a K value, if I write 2, if I write 3, if I write 3, if I write 6, then for every one of them, I have to be able to set up an equilibrium expression, and it's going to have to mirror the chemical reaction that takes place. In every case, the removal or the addition of a proton. And we'll look at the systematic sort of formal way of doing that in a moment. But appreciate that all I'm really doing here at this moment is understanding that for every number of proton or basic sites, acidic or basic sites I have to have a K value associated with it, and that's what makes things more complicated.